Okay, so quadratic reciprocity is a theorem that I stated before and you would have used to solve one of the homework problems. And what it does is it relates whether or not P is a square mod Q to whether or not Q is a square mod P. It's a connection between two very different things. So you kind of think of the whole world as stuff mod P, or some prime P, and then there's a whole other world as stuff mod Q, or some other odd prime Q. Then what quadratic reciprocity does is it somehow establishes a link between two kind of very different worlds. So, I mean, the stuff that's going on here is completely different than what's going on here. And it depends a lot on properties of the prime Q and P, but somehow there's a link between these two. What you get from quadratic reciprocity. I'll restate the exact result. My goal is to give a complete proof of omitting nothing of quadratic reciprocity using the theory of Gauss sums. If you look at number theory books or number theory courses, they often sort of divide them into two categories. Those that contain a proof of quadratic reciprocity and those that don't. So it's somehow like a deeper theorem than most of the other theorems that you would see in a number theory course, in an elementary number theory course. But it's still accessible to what we've done so far, okay? So our goal is to completely prove, nothing omitted, quadratic reciprocity. Prove the theorem that Gauss proved in a million different ways long ago. And this is, the formula is easy to state, but there is no kind of ridiculously simple half-page proof that doesn't assume a bunch of other things, which would make it many pages long, of this statement, even though there are many different proofs of it. So our goal is to give a proof. It's a deeper thing than I've proved anywhere else in the class. Maybe deeper than what you've seen in most other classes. Yes? I don't know. I don't think so. I think it's a later proof. There are more elementary proofs, but this is the most natural one by far. It's pretty conceptual, and it's one that you can basically remember the basic idea and kind of figure out, unlike some of the other proofs, which are just very technical but elementary. Okay? And it also introduces various objects that are useful in and of themselves. And quadratic reciprocity itself kind of just looks like a funny formula, but it itself is a reflection of something that is much, much more general, called class field theory. It's really just a special case of something called class field theory for quadratic fields. Okay, so that's our goal, and I won't be able to do all of this today, but because so many people canceled their presentations, I will also talk on Monday. So what I'm going to do is prove quadratic reciprocity modulo some very plausible propositions about sums of roots of unity, which I'll state first, and then on Monday we'll prove those statements. Okay? So today you'll get a proof that's complete modulo in assuming some very elementary sounding statements about sums of roots of unity. Okay? So that's the structure. So part one, prove this, then part two, establish some background facts about Gauss sums. And if we somehow don't have enough time to prove everything, then at least you'll have a general sense of how the proof works, and you'll only be missing some calculation involving some roots of unity, which is completely straightforward to just read. But hopefully we'll be able to do the whole thing. It's like 5 pages of my notes. Okay, so first, I'll introduce Gauss sums. So it's a really cool idea. So let me give the definition and tell you how these are going to work in the proof. But we're going to use complex numbers, and let zeta sub n denote e to the 2 pi I over n, or cosine of 2 pi over n plus I sine of 2 pi over n. This is an nth root of unity. It's a number that when you raise it to the power of n, it gives you 1. So it's a root of x to the n minus 1 equals 0. But no smaller power gives you 1. It's an element of the complex numbers, and it has a multiplicative order n. And so if you drew a picture of the complex plane like this, then an nth root, let's say a 4th root of unity is right here. This is n equals 4. That's, of course, I in the complex plane. An 8th root of unity would be right here. zeta sub 8. Okay. So I guess I guess this is 1/2 or 1 over root 2 plus I 1 over root 2. So they're complex numbers that have order exactly n. So that's what I mean by zeta sub n. So how could complex numbers be useful? Well, check this out. So here's what you're going to do. So fix an odd prime p. And consider, and for each a, an integer, define g sub a. The g is for Gauss. G sub a it's a sum of these roots of unity that encodes the values of the Legendre symbol. So it's a sum as n goes from 1 through p minus 1 of n on p zeta sub p to the power of n. So these zeta p's, this is just a sum of some complex numbers where you have some coefficients. So this is just a specific complex number. But also algebraically, it's formally a sum of roots of unity. And in the book, by the way, I often include 0, but it makes no difference at all because 0 on p is just 0. Let me remind you about this notation. N on p is 0 if p divides n. It's 1 if n is a perfect square that's not 0 mod p. And it's minus 1 if n is not a perfect square mod p. And a statement that I'll prove in a moment, and which I mostly prove the background for, namely the fact that fp star is cyclic, is that this is nothing more than just n to the power of p minus 1 over 2 modulo p. This number that's 0, 1, or minus 1 is congruent to n to the p minus 1 over 2. Okay, so that's what these numbers are right here. So g sub a, the Gauss sum g sub a, is a formal linear combination. Well, it's just a sum of powers of all the powers. Well, yeah, because you just run through 1 to p minus 1 of all the interesting powers of zeta p, and the coefficients are plus or minus 1. Okay. So it looks like something like maybe zeta minus zeta squared plus zeta cubed plus zeta to the fourth, etc. It encodes information about this algebraically. And these two in a second. By the way, here's what quadratic, well actually, I'll come back to that, I'll just state it in a second. So here's some facts about these Gauss sums, which called proposition 1 and proposition 2. So proposition 1 gives you a kind of flavor for what these things are like. It says that for any a in z p not dividing a, you have that g a, that's the sum I wrote down right there, that complex number. If you square it, so that complex number need not, well, you'll see, is this j squared is minus 1 to the power p minus 1 over 2 times p. So that's a proposition. I have not proved that yet. We're not going to prove it today. We're going to prove it on Monday. But let's look at it for a second. It tells you a couple of things. It lets you answer at least 2 questions. 1, is g sub a an integer or not? Is it an integer or not? You can answer that from the proposition. With a not equal to, if a is not divisible by p, is g sub a an integer or not? Quick, because I have a lot to say today.
Yes.
Wait, yes?
Yes.
Okay, you're wrong. All right, next. Somebody else try.
No.
You're right. Because look, the square of g sub a is a prime times plus or minus 1. And primes are not perfect squares, or whatever. I mean, if you just take the square root of both, a square root of both sides, you get ga is some, it's possibly I times square root of p. And p is a prime. Square root of p is then not an integer. Okay? So this thing, whatever it is, it really is like a square root of p. So it's kind of like, it has absolute value square root of p. So that's the kind of thing to think of it as. Remember, if you take all the powers, because with complex numbers, when you multiply them, it's the same as adding the angle. So the numbers that appear in the sum here are, they look like a wheel on a car, like this. And so with each, what you're doing is you're adding up all these complex numbers with various signs. So you're adding and kind of randomly adding and subtracting this collection of complex numbers, and it turns out you end up with a number that has magnitude square root of p. That's what that statement tells you, for example. So it's like, you know, it might be way over here or something. It has magnitude square root of p. So that's one thing it tells you. Here's another funny thing. Does g sub a even depend on a? Very much. It doesn't, because look, on the left you have g sub a, and on the right there's no a at all. So, I mean, it does depend a little bit on a, but all it really depends on is whether or not p divides a. If p divides a, then it's just 0, as it turns out. G sub p is 0, but when p doesn't divide a, it's that. So it doesn't even depend on a. Okay, which brings me to proposition 2. Which is g sub a is equal to the symbol a on p times g sub 1. So actually, g sub a itself does depend on p, but the square of g sub a doesn't. That's what we saw here, that the square of g sub a didn't depend on p. G sub a depends on, sorry, a. G sub a squared doesn't depend on a, but g sub a does, but it's just up to sign. So actually, wasn't quite what I just said. But the right-hand side here doesn't depend on p, so g sub a squared doesn't depend on, say, p, on a. And so here you see that there's this relationship. So this will be some work to prove, but we'll prove it. This is actually not too hard to prove. So the Gauss sum g sub a, it's basically just a multiple of the Gauss sum g sub 1. It's, I mean, just to give you a hint as to why that's true, I clearly defined this incorrectly because there's no a over here.
I was wondering about that.
Yeah, there should be an a right here. Sorry, I just didn't write it down. Otherwise, it really doesn't depend on a, which would be really stupid. So yeah, there's an a right here. So what you do is you permute around the zetas, depending on a. But the thing is, if you replace a by another, like a b that's also coprime to p, the two differ by some rescaling that's an invertible mod p. So you can easily kind of get from one to the other, and exactly what ends up happening is you get this popping out. We'll prove that later. Okay? So that's it. Those two propositions are really all we need to now prove quadratic reciprocity, plus this statement right here, which I should really explain. Which, let me formalize that as kind of a proposition. So let's call it proposition 0, namely that in general, a on p is a to the power of p minus 1 over 2, corresponding to that mod p. Okay, so here are 3 propositions, and now let me tell you the law of quadratic reciprocity again. Okay, so here's the theorem. Of Gauss. It says the following: if you have odd primes p and q, so say distinct odd primes, then here's the amazing thing that happens. Whether or not p is a square mod q is related by a simple formula, namely the symbol p on q. It's minus 1 to the p minus 1 over 2 times q minus 1 over 2, and then q on p. In other words, something mod q is related mysteriously to something mod p. And the way we're going to prove this today, assuming those 3 propositions, which we'll prove right after we use them, I'm going to recopy the definition of the Gauss sum over here. It's pretty important. This is for the Gauss sum is sum n equals 1 to p minus 1, n p zeta sub p to the a n. It's a complex number, the sum of pth roots of unity that encodes the Legendre symbol, all the values of the Legendre symbol. So the way we're going to prove this, more or less, is we're just going to do various arithmetic tricks with and use identities involving this Gauss sum. What we're going to do is we're going to take the Gauss sum for p and work with it modulo q. Or you could do the whole proof by taking the Gauss sum for q, so we use a qth root of unity instead and working modulo p. Either way, you end up with the same result. So that is, in one sentence, our proof of quadratic reciprocity. So if you're really obnoxious, you might say proof, easy, just consider stuff with G sub A's where it's the Gauss sum associated to P, like over there, so involving pth roots of unity, mod Q, involving zeta P, mod Q. Or the other way around. So what we'll do is we'll prove that this identity holds modulo Q. Like that this number, which is 0, minus 1, well actually it's either plus 1 or minus 1, because P and Q are distinct primes. We're going to prove that the left-hand side is congruent to the right-hand side mod Q by just doing a bunch of little clever stuff involving Gauss sums, basically involving those three propositions, all modulo Q. And if this number, which is plus or minus 1, is congruent to that number, which is plus or minus 1 mod Q, then these two numbers are equal, because Q is odd, since these are odd primes. Okay? That's the structure of the proof. And the clever stuff, believe it or not, this stuff, it's not really that hard. I think I'll easily be able to show you the proof modulo these propositions. It's actually more work to prove this right here than it is to finish proving quadratic reciprocity. So the cool thing is this very plausible looking thing. Well, I don't know if it's plausible to you or not. Let's do one example of proposition 1, just so you believe it's plausible. And then we'll deduce quadratic reciprocity. So what's the simplest possible example of proposition 1? Well, that would be p is equal to 3, the first odd prime, and a equals 1. Example. And what does it say? Well, I mean, these propositions are just statements about G sub A. The bottom one is really boring with A equals 1. So let's look at the top one. So G sub 1. Well, okay, so what's going on here? First, you have to worry about what the heck is zeta 3. So zeta 3, it's a cube root of unity, so its cube is equal to 1. So it satisfies the polynomial x cubed minus 1, which factors as x minus 1 times x squared plus x plus 1. And zeta 3, it's not a root of x minus 1, it's a root of the other factor. So zeta 3 satisfies, I'll just call it zeta henceforth. Zeta satisfies zeta squared plus zeta plus 1 equals 0. So whenever you're doing arithmetic with zeta, you can always replace it by, you can always replace zeta squared by minus zeta minus 1. Alternatively, you could write everything in terms of complex numbers and stuff, but this is easier. Okay, so that's what zeta is, and now let's just write down the definition of the Gauss sum G sub 1. G sub 1 is the sum of, well, first it's 1 on P is 3, times zeta, and then it's plus 2 on 3, that symbol, and then zeta squared, because A is just 1, and this is n equal 1 and n equal 2. Okay? So let's just figure out what this is. Is 1 a perfect square mod 3? Yes. So that's zeta. And is 2 a perfect square mod 3? No. So this is our Gauss sum. It's just zeta minus zeta squared. But zeta squared is minus zeta minus 1, so I can write that as zeta minus zeta minus 1. Seems wrong. 2 zeta plus 1. I don't know if it's wrong or not. It is what it is. Seems really simple, so it's hard to have made a mistake. So there you are. Maybe I'll just check my notes. I don't know why I'm worried. Here's a good example. That's exactly what my notes say. Okay, good. So there's our Gauss sum. Proposition 2 says something about its square. This is just some complex number. Its square, though, is supposed to be an integer. So let's see. G1 squared. Right? This thing right here. So G1 squared, well, let's just take 2 zeta plus 1 squared. So we get 4 zeta squared plus 4 zeta plus 1. Zeta squared is the same thing as minus zeta minus 1. So this is minus 4 zeta minus 4 plus 4 zeta plus 1. Hey, look, that's minus 3. Woohoo! Because that's plus or minus p. And moreover, the sign, I hope, is minus 1 to the p minus 1 over 2. And it is, because 3 minus 1 over 2 is 1. So this is, in fact, exactly as predicted. Minus 1 to the 3 minus 1 over 2 times p. Okay, so proposition 1 just says that always happens. And we'll prove it on Monday, and it's really, really hard actually to prove. But see. Just to give you a sense of what's involved, it looks like real math. That's the part of the proof of proposition 1. So, lots of sums. We'll do our sums. Okay, so now let's prove a quadratic reciprocity. Okay? So this was just meant to convince you that these propositions are reasonable, and they're just talking about these really algebraic objects, just sums or roots of unity with signs. Okay? And when you square them, things cancel out, and you end up with nice integers. Stuff like that. Right? Any questions before I do the proof? By the way, here's the entire proof. So it's not like some. This is the proof of quadratic that I'm about to give on the board. So it's just some tricks and stuff. This is the stuff. Okay, any questions before we get going? Right, so let's try to prove quadratic reciprocity. Okay, this good. Not much better. Still best. Okay. Alright, so let's define P star to be minus 1 to the p minus 1 over 2 times p. Just a definition. I've never mentioned p star before, ever, until this very moment. Remember, our objects are 2 primes p and q, and our strategy is we're going to just do some clever tricks modulo q with Gauss sums to get something that tells us that these two numbers are congruent modulo q. That's the structure of the proof. All right, so here we go. So first, let's also define g to be g sub 1. We're using the Gauss sum. All these Gauss sums involve p roots of unity. So when I say g sub 1, I mean the Gauss sum, which is sum n on p zeta sub p to the power of n equals 1 to p minus 1. Okay? It's that complex number. That's what g is. So now I have a number p star and a number g. And of course, this is just plus or minus p. Okay, first, g squared is p star. That is proposition 1, right? Because this is true for all the a's that are not divisible by p. So in particular, it's true for g sub 1. It says g sub 1 squared is minus 1 to the p minus 1 over 2p. Okay, so this is just proposition 1. So we're kind of assuming it for the moment, and then proving things assuming this. Okay, now it gets interesting. So it's a really critical equation, so I will not put it directly in front of the lectern. Okay, so here is an observation. P star on Q is P star to the power of P minus 1 over 2 modulo Q. which is just proposition 0 applied to P star. Okay? Which again, I haven't given a careful proof of yet. I only established, what I did was I proved that FP star is cyclic, which is the main input to proving this, but I still think that this requires some work, which we'll do later. Okay, so using proposition 0, we have that. And now, it's interesting. So let's go back to G again, right here. So look what happens if you take G to the power of Q minus 1. Then, just looking at what we have here, oh, this is pretty funny. So Q is an odd prime, so you can write this as G squared to the power of Q minus 1 over 2. But G squared is something we know about. So let's use that and write this as what it is, P star to the power of Q minus 1 over 2. Okay, that's all true. But it's kind of annoying because it's G to the Q minus 1. Guess what we're going to want to do? The main trick in the middle of this is going to be that when you take x plus y to the power of q, it's x to the q plus y to the q when you're working modulo q. That's going to be like the central trick to this whole proof. And that's a q minus 1. So let's just take both sides and multiply by q. So, except, yeah, so, I mean, pretty much that, just g to the power of q is now equal to p star to the q minus 1 over 2 times q. Okay. So on the left-hand side, I have this Gauss sum, this complex number, involving zetas, raised to the power of q. And on the right-hand side, I have the integer q times p star to the q minus 1 over 2. But p star to the p minus 1 over, oops, okay, just, that is what it is. I mean, okay, everything I said is true. Then, okay, so let's do another thing. Okay, so this is what g to the q is, but it would be nice to have, this is what is confusing me. That is not a p, it's a q, because I'm applying this result, but notice the denominator is q, so the power you have to raise to is q minus 1 over 2. That was throwing me off for a minute there, because it just didn't work. So that is p star to the q minus 1 over 2, not p star to the p minus 1 over 2. Okay, so now, that's much better. So, so now look what you can do. Let's see. And then this is a congruence, so be careful about that. So now, yeah, so now I'm going to rewrite this as, and also I multiply both sides by g, and for some reason I wrote a q there. What the hell I'm doing? Okay, so I multiplied both sides of this equation by g, and that's this equation. Before, I had put a p there, which made no sense, and I also had something that had nothing to do with this, which also made no sense. Okay, so now it's all right. So now we have this, but there's a connection here. We can use the other side if we want. And we will. So let me write this as p star, just always working mod q, p star over mod q times g. Okay, so this is pretty useful. What we have is well, we have this g to the power of q, and g is something that we can expand it out, and we can use that we're raising something to the power of q modulo q, because everything here is mod q. And what we'll end up with, so this is going to be the next step, we're just going to take this thing right here, and we're going to write it as something else using the identity x plus y to the power of q is congruent to x to the q plus y to the q mod q. Because all the other terms in the middle are divisible by q. You remember that from a homework problem, hopefully. And so we're going to rewrite this, and we're hopefully going to get something that involves something flipped over right here. And then we'll be able to cancel the g's from both sides and end up with what we want. Okay? So that's the idea. You sort of follow your nose idea at this point. And it will work. So we're going to take g to the q and just rewrite it. We'll do it right here where the example is, so you can see. I guess I can probably put it right here. So that's visible. I'm just going to take g to the q. G is this sum. So I'll take this sum. Sum n equals 1 to p minus 1 n on p zeta to the n whole quantity raised to the power of q. That is just the definition of g. But I'm going to expand it all out, reducing everything modulo q as I go. What that means, by the way, is when you're working with these roots of unity, you get to take the coefficients modulo q, and you have that. You maybe worry a little bit about the algebra involved in that, but it's all solid. Okay, so we just expand it out, but using that modulo q, it's really, really easy to expand out. Look, it's just sum n equals 1 to p minus 1 n on p to the power of q times zeta to the n q, right? I've just used exactly this, except with instead of 2 terms, I used it with n minus or p minus 1 terms. And I'm working modulo q. Okay? But look, this looks a lot like the Gauss sum g sub q. Because look, I mean, the difference between g sub 1 and g sub a in the definition here is that you raise zeta to the power of a. So let's make that out. Also, n on p, this is plus or minus 1. And so if you raise it to the power of q, that does absolutely nothing, because q is an odd prime. If you raise minus 1 to an odd power, it does nothing. So we can just rewrite this as sum n equals 1 to p minus 1, n on q, and then zeta to the qn. And now it's exactly this. So it is just g sub q. So this is all modulo q. So g to the power of q is congruent modulo q to g sub q. But g sub q, this is really awesome. It involves the other Legendre symbol, the thing we're trying to relate things to. So let's write that. This is equal to q on p g sub 1, which is just by definition g mod q. So at this point, we should get really excited, because what's happened? On this side of this long sequence of equalities, we have a Legendre symbol with a q at the bottom. And if you trace it all the way through, it's equal to a Legendre symbol with a p at the bottom. We're like at the home stretch at this point, because those are the two things we want to connect. And the connection is taking a Gauss sum for p and reducing it mod q. Or if you didn't, you could do the whole thing with p and q switched, of course, which would be identical. Because p and q are abstract primes. Okay, so now on both sides, we can cancel the g. It's invertible mod q because g squared is p up to sine, and p is coprime to q. So you can cancel it from both sides. Again, there's a slight algebraic subtlety which might concern you, namely that we only develop the foundations of working modulo q when q is, like when you're working with integers mod q. And here you're working with algebraic integers modulo q. But everything's fine because p and q are coprime. So it's valid to cancel g from both sides. So if you cancel g, you get, just summarizing this, you get p star q on q is congruent to q on p mod q. And now either we've made a mistake or we've just nailed it and we just need to unwind some definitions. Okay? So we want this statement up here, and we have this. But at this point, it's pretty easy because this symbol A over P is a homomorphism. So X goes to, or A goes to A on P. That defines a homomorphism from FP star to plus or minus 1, which is, let's say, it follows immediately from knowing that it's this powering map. So all we have to do is just take P star, replace it by what it's defined to be, use that we have a homomorphism, and we'll end up with this right here. So let's do that. So notice that P star on Q is, so what is P star? It's minus 1 to the P minus 1 over 2 times P on Q. But the symbol, something on Q, it's a homomorphism, which means that you can, that means that if you apply it to, if you do AB on P, that's exactly the same as A on P times P on P. It's multiplicative, like an arithmetic function, even better, in that you don't have to be co-prime or anything like that. Doesn't make any sense here. So this is the same thing as minus 1 to the power of P minus 1 over 2 on Q times P on Q. So P on Q, that's something kind of fundamental that we're interested in. This other thing, though, is just a number. You can raise it to the power of the denominator thing minus 1 over 2 and evaluate it. And so here's what you get. It's minus 1 to the P minus 1 over 2. That whole thing raised to the power of Q minus 1 over 2. All times P on Q. But wait, what have we done now? We have minus 1 to the P minus 1 over 2 times Q minus 1 over 2, that's what this is, times the Legendre symbol P on Q, is equal to, if you just look at what we just did, to Q on P. That's exactly the quadratic reciprocity theorem of Gauss right here. So we just proved it. And the only thing that I haven't explained to you is why these little identities involving roots of unity hold. Okay? But everything else, I haven't omitted any steps at all. It's all here. Okay? Any questions? Is it really clear? So just stepping back for a second, all it really is you want to see that these two things are the same. They're plus or minus 1. So it's enough to work mod Q. And what you do is you consider this Gauss sum mod Q raised to the power of Q. And that's like a natural thing to do because it's a sum, and you can apply the freshman dream, as it's called. With some people to evaluate it, and it ends up just naturally turning into another Gauss sum, right, like this. And it turns out that that other Gauss sum, by something we have not proved yet, but is actually pretty easy, is related to the other Legendre. Well, it's just related to this Legendre symbol. And so somehow by working mod Q, the Legendre symbol with a P on the bottom pops out naturally because, after all, the Gauss sum associated to P, which is the ones we're considering, these Gauss sums associated to P, they all involve the Legendre symbol over P. But on the other hand, the Legendre symbol with a Q in the bottom is a power of P star. It's related to a power of P. And a power of P is also related to the Qth power of G, like this. Because of the other proposition, namely that a power of G gives you P. So the Legendre symbol with a Q on the bottom comes from a power of G because of this thing right here, and this, but mainly because of this. And on the other hand, a power of G can be computed and ends up giving you a Legendre symbol of P at the bottom. So basically this Gauss sum, just if you stare at it in two different ways, on the one hand, computing a power of it gives you a Legendre symbol with a P on the bottom. That's using the freshman's dream. On the other hand, computing a power of it using this alternative interpretation of the Legendre symbol gives you a Legendre symbol with a q at the bottom. And if you just do the arithmetic, you end up getting exactly the law of quadratic reciprocity. So that's the proof. And the only thing that's missing now is like basically the theory of Gauss sums, which is these three propositions. Well, really these two propositions. Okay, and I'm not sure. I think I'm gonna. I mean, I tried to prove it in 30 seconds last time, but I'll try it again to show you why that's true in the remaining moments. Let's see. It's actually pretty easy. So proposition 0. So why? So what's going on here? So FP star is cyclic. That's what we spent a lot of effort one day proving by looking at polynomials, which means that there's some element g in FP star so that the elements of FP star are g squared up through g to the power of p minus 1, which is just equal to 1. This last one is equal to 1. Okay? Let's just take all those numbers systematically and square them and see what we get. Just see what happens. And it's just so amazingly clean. So look, just square. So what happens? If you take g and square it, you get g squared. If you take the next one, g squared and square it, you get g to the 4th. And you just keep doing this. You get up to, it starts getting interesting when you get up to g to the p minus 1 over 2, and you square it. Because what do you get? You get g to the, yeah, you get 1. You get g to the p minus 1, which is just 1. Okay, the next one is g to the p minus, or g to the p plus 1 over 2. It's just the next number after p minus 1 over 2. If you square that, you end up with what? You end up with g squared, because the g has multiplicative order p minus 1, so you're always taking the exponent and reducing it modulo p minus 1. And so if you keep doing this, as you go, you get g squared there, then you get g to the 4th, and you end up going all the way up to g to the p minus 1 again, just 1. So those are the squares. They're exactly, so these squares are g to an even number, where that even number is between 2 and goes up to p minus 1. Okay? That's what the non-squares are. They're everything that's left over. Everything that wasn't a square has to be a non-square. But you know exactly what the other ones are. The non-squares are g to an odd power. It's really, really nice and simple. Or 1 less than or equal to the odd number less than or equal to p minus 1. I guess I could put a 1 there too. Okay? So that's really, really nice. If you fix a generator g, then the squares are exactly the even powers, and the non-squares are the odd powers. From which this should be clear. But you have to think a little more about it. But it's just, if you take g to the power m, and then raise it to the power of p minus 1 over 2, you're just asking whether that's plus 1 or minus 1. And it's plus 1 if and only if that m has a 2 in it. Otherwise, you're going to raise it to a power that it's not a multiple of p minus 1. So it's plus 1, so this equals plus 1 if and only if p minus 1 divides m times p minus 1 over 2. Not the Legendre symbol, but the product. M times p minus 1 over 2. Okay? And from elementary number theory, you know that there's no way p minus 1 divides this unless m is even. So m being even is exactly the same as this being plus 1. And that's exactly proposition 0. So that is actually proof. Okay? Alright, so all we have to do on Monday is prove propositions 1 and 2. That's it. But it will involve that enormous calculation with triply nested sums and stuff like that. Believe it or not. Yes? Dang! Why? It's so interesting.
Yeah, I didn't go far enough.
Well, in a presentation, you could just give like a proof of Fermat or exponent force.
Finally got some sun.
Just the it's really just sketching the proof.
And then
Puddle.
Yeah, just give like the